In this video, we're going to cover identifying other variables that might be present in a bivariate data plot. So, just a reminder that on a bivariate graph, we're interested in the correlation between the explanatory variable and the response variable. This video is going to cover correlation versus causation, groups within the data, confounding variables, that's variables that affect the response, and lurking variables, so they're variables that might affect both the explanatory and the response variable. In this first example, I pulled this graph off the internet, so I don't know if the data is real or not, but we've got a number of firefighters that are attending the fire and the damage that's caused by the fire, and we can see that there's a strong or a moderate positive relationship between those two variables. So we can see that there's a correlation. So as the number of firefighters increases, the amount of damage done by the fire is also increasing. But that doesn't mean there's a causation. That doesn't mean that if we increase the number of fires, then we're going to get more damage. If that was the case, then the fire brigade could say, well, actually, we don't want very much damage being done, so at the next fire, we're going to send just a very small number of firefighters. So causation can only be shown in a controlled experiment. So for example, if we had an explanatory variable which was the amount of fertilizer used, and the response variable was the amount of growth in plants, we control how much fertilizer we're putting on each plant, and we could measure the response. And so we could say, if we found a correlation between the amount of fertilizer and the growth, we could say that the fertilizer was causing the growth. But that's only because we had a controlled experiment. If it was an observational study, so if we're observing the firefighters and the damage being done at each of these fires, but we're not controlling them, then we can't say that there's causation between the variables. In an observational study, there may be confounding variables, so that's variables that affect the response. For example, there might be weather. So if it was a rainy day, then maybe less damage is being done by the fire. And when I thought about it, I actually found it very hard to find confounding variables for this example. The other sort of variable that may be present is a lurking variable. So that's a variable that affects both the firefighters and the damage. So for example, the seriousness of the fire. So if the fire was very serious, then we might send more firefighters and it might be causing more damage, and that the lurking variable might be causing the causation rather than the number of firefighters. I also thought maybe the location could be a lurking variable. So if the fire was in Auckland, for example, we can send lots of firefighters and the buildings are really close together, so it might cause lots of damage, as opposed to if it was a rural fire in the outback of Oamaru, maybe we just can't send as many firefighters there, and even if the fire was quite large, it wouldn't be doing very much damage. So confounding variables might affect the variation in the damage or the response variable, and they might affect the strength of the relationship, and lurking variables may be responsible for the causation between the explanatory and response variables. Now I'm going to look at an example. I'm going to bring an example up on NZGrapher. So right now we've got diamond price versus weight, and we can see that as the weight increases, the variation is getting more. So we can use the color by feature to see if we can identify why that might be. So if we look at clarity, for example, we can see we've colored by clarity, and we can see the clarity is above and below the line of best fit, and so maybe that isn't a confounding variable. If we look at color though, we can see that the diamonds are given a color rating from 1 to 6, and the diamonds that have got the color rating 1 in general have the highest price, and those that are rated 6 are given quite a low price. So what we could do is we could separate the diamonds into groups by color. One way to do that is to create a new variable. So I'm going to create a new variable from a condition. The condition's based on color. If the color is less than or equal to 2, then I'm going to say they're color 1 or 2. create a new condition, so less than or equal to 4. This is going to be 3 or 4. And the last condition will have colours 5 or 6. So what NZ Graph does is it looks for this first condition first, then it'll only look for the second condition in the variables, in the rows that haven't already been met by the first condition. So I'm going to create this new row. And so we've got colour by condition, and for variable 3 we can go colour by condition. What that's done is it's split the data into 3 different subgroups, and it's fitted a model to each of those groups. And so by using 3 different groups for our data, we can see the variation above and below the line of best fit is much less, so the strength of each of the relationships is much stronger. So just to recap, for excellence, we can use the colour by to visually identify groups, and we can use the variable 3 to subgroup and create separate models for each subgroup of data. So what we've done here is we've identified a confounding variable. So the colour variable has affected the price of the diamonds, and so by separating them into groups by colour, we've removed the confounding variable and we've fitted the 3 different models. So for excellence, we want to reflect on the benefits of having multiple models, or we might just want to look at the models and look at the differences between the models. So just one more point there. If we have categories, we can merge the categories by going sample and then create a new category by regrouping. And what we did here is for a numeric variable, we've gone sample and then create a new variable by condition. So we've created a category variable and it's been by condition. The last example I want to look at is kiwi weight by height. So what I'd expect to see is as the bird gets taller, I'd expect it to weigh more. And so we've got a positive relationship, but it's really quite weak. Weak meaning there's lots of scatter above and below the line of best fit. So I can see 2 quite distinct groups. So if I just put a circle around there and then there, I've got 2 quite distinct groups within this data plot. And so what I'm probably seeing is I'm seeing 2 categories that could be male or female, or it could be something else. So I'm going to use the colour by, whoops, undo, stop. So I'm going to use the colour by and we'll separate them by gender. And what that tells us is actually the 2 groups aren't by gender, although we do have 2 groups by gender. Possibly we need to separate them by species. And so we've got 3 species of kiwi here. We've got the red ones, the great spotted kiwis, green, which is the North Island brown, and the blue kiwis, which is the tokoeka. And so what we can do is maybe we'd like to look at one of those groups and in more detail. To do that, we're going to create a sample. We're going to sample by species, and we're going to remove the kiwis we don't want. And so what this is doing is it's taking a sample from the original data set. I've asked it to take no great spotted kiwis, no of the tokoeka, and I've taken all of the North Island brown. So the sample now only contains the 1 species, and then I can separate it by gender. And so I can say for these North Island brown kiwis, there's definitely 2 subgroups by gender. So the females are much taller and are much heavier than the males. So I might want to use variable 3 and separate the genders out for 2 different models. And what I can see here is really quite interesting. So these models say there's no relationship between height and weight. So we'd expect as the kiwis get taller that they'd weigh more, but in actual fact there's no real relationship there. And what we're probably seeing is there's other variables at play that are affecting the weight. For example, how readily available their food source is, or maybe there's some other things to do with their body condition or the time of year, or there could be a number of variables and we just don't know what they are. So to recap there, we've used the colour by to visually identify the groups. We've used sample and then sample to remove groups that we don't want to look at, and so we can look in more detail to some groups. What we've got here is the causation between, I'll say that the relationship between height and weight may be just because of a lurking variable, and this lurking variable is the species. When we looked at the second graph, so we've subsetted the data and then grouped it by gender, we can see that there's no relationship here. So we've identified there may be other confounding variables that are affecting the variation, so the variation in weight or the strength of the relationship. So that's just showing you how to drill down into the data and look at it in more detail. So these are excellent skills. So I will finish there. Thank you.